So at the end of the previous video, I ended with saying that I just wanted to also, and then I didn't do what I wanted to also do, which is I want to generalize this. So this is for two random variables, x and y. We want to be able to do an arbitrary number of random variables. So this concept here is called pairwise independence, because this pair of random variables is independent. So this is pairwise. Oh dear, pairwise independence. Okay, so let's now look at the concept. Let's look at the generalized case. So in the generalized case, we will have our random probability space, omega f and p, and we will have an arbitrary number of random variables. So let's say x1, x2, all the way up to xn, where they are all mapping it onto standard probability spaces. Then the criterion for independence of all of these random variables is that the probability that x1 is less than or equal to some little x1, and x2 is less than or equal to little x2, and x3 is less than or equal to little x3, all the way up to and xn is less than or equal to little xn, is equal to the probability that x1 is less than or equal to little x1 times the probability that x2 is less than or equal to little x2 times all the way up to the probability that xn is less than or equal to little xn. And similarly with the case of the discrete independence, if all of these, all x1, x2, all the way up to xn are pairwise independent, i.e. x1 is independent of xi, I is equal to 0, 1, 2, all the way up to n. Oh, sorry, not 0 and 1. It only matters for 2 to n. Obviously, we don't need to make it independent to itself. And x2 is independent of all the others. All the way up to xn is independent of all the others. So basically, pick any two, and whichever two you pick, they are independent. It does not imply that they are all independent. In this way up here. So this, if they are all pairwise independent, it does not imply that they are actually independent, that they are totally independent in this way. And a key example that I can show you of that is, let's just take a discrete case. So let's take the random variables. So let's have a probability space which is just, you flip a coin twice. So on your first one you can get a heads, on your second one you can get a heads, on your first one you can get a heads, or on the second one you can get a tails. Tails first, then heads, and then tails. So those are all the possible outcomes of flipping a coin twice, assuming of course that it doesn't land on its side. Okay, so we can set up some random variables. So we'll set up the random variable x1, which is going to map s onto, it's going to be a Bernoulli random variable, so it's going to map it onto 0, if you get a tail first, if tail first, and 1 if head is first. So it's basically going to map these two here, so the ones where you get a head first, it's going to map them onto 1, and it's going to map these two where you get a tail first onto 0. We've then got another random variable which is x2, which again is going to map you onto, it's going to be a very similar random variable, so it's going to map any outcome onto, again, 0 and 1, and it'll be 0 if the second flip is a tail, if second tail, and if first, and second, and 1 if your second flip is a head. So it's going to map this one onto a 1, it's going to map this one onto a 1 because your second flip was a head, it's going to map this one onto a tail, and this one onto a tail. And then, we're going to have a third random variable, x3, and x3 is going to map s onto, it's going to map it onto 0 if the two flips were different, if you got heads or head tail or tail head, and 1 if they were the same, so if you get head head and head tail. sorry, tail or tail or tail. Right, now, these are evidently not independent, because if I know the value of x1 and I know the value of x2, then I can work out the value of x3, because if x1 was equal to a 1, you know that you got a head first, and if x1 was a 0, you know you got a tail first. And then similarly here, you know whether you got a tail or a head, so you can work out whether both of these were the same, i.e. you got two zeros, or you got two ones, or whether they were different, you got a 0, 1 or a 1, 0. And then you can work out x3. So they're evidently not all independent. However, x1 is certainly independent of x2, because knowing what you got on your first flip certainly doesn't affect what you get on your second flip. And indeed, x1 is independent of x3 as well, because knowing what you got on your first flip doesn't tell you anything about whether you're overall going to get two flips of the same thing, or you're going to get two different things, because it doesn't tell you anything about what you get in your second flip. So again, these two are independent, and similarly these two are independent, because knowing what you got in the second flip does not tell you whether they were the same or not. So these are all pairwise independent, and you can, in fact, if you want, you can check that all of these satisfy the equivalent. Oh, and I just want to mention something else. This law here, which I wrote down that you could use for the continuous case, this also works in the discrete case. It is simpler to use the discrete one in terms of the probability mass function, but this one works in both the continuous case and the discrete case. So it's in a way more general, but the probability mass function, you could use that here. So you could show that the probability that x1 is equal to x1 and x3 is equal to some little x3 is just equal to the probability that x1 is equal to x1 times the probability that x3 is equal to x3. And you could show this for any two, i.e. you could let this one equal 2, and set these all equal to 2, or you could let this one equal 2 and let this one stay as 3. So you could show that for every single one of these, they are pairwise independent. But what is not true, it's not true that the probability that x1 is equal to x1, x2 is equal to x2, and x3 is equal to x3 is going to be equal to the probability that x1 is equal to x1 times the probability that x2 is equal to x2 times the probability that x3 is equal to x3. And that's quite easy to see, because each of these is Bernoulli distributed with probability a half, because it's equally likely that you'll get a 0 or a 1 in each of these. So let's set this equal to the probability that x1 is equal to 1. So let's look at a specific example. The probability that x1 is equal to 1 and x2 is equal to 1. So that means we got two heads, but then let's set it equal to the probability that x3 is equal to 0. Now, of course, that probability is equal to 0, because if you got a 1 on this one, you got a head first, and if you got a 1 on this one, you got a head second, so you got this. But that would be ascribed to the value 1 here, because they were both the same. And we're asking for the event that x3 was also equal to 0. So the probability of that should be equal to 0. But this is formula. If this formula was true, it would tell us that it was the probability that x1 was equal to 1, which is a half, and times the probability that x2 is equal to 1, which is again a half, times the probability that x3 is equal to 1, which is again a half. So it would be telling us that this was an eighth, which is absolute nonsense, because this cannot happen. It's utter nonsense.